Greetings, physicists. This video will be about solving problems that involve kinetic energy. So we will start with this an old canal boat. And the horses are pulling it. They pull it up to a certain speed, and it takes a long time because it's got a lot of mass. Or it takes a long distance is what we're going to actually measure this with. And there's no angles in this. That's an important thing. The rope is straight and level. And when we're looking for distance, how much distance? So whenever I see distance in here, I think, well, this is a work problem. The horses are doing work. They're doing F delta X of work. But they're trying to get it up to a speed of 0.7, so we will also need to do a kinetic energy equation, which is that the work they are doing is causing kinetic energy, or 1/2 mv squared. And technically that's a V final minus a V initial, but we know that the boat is starting from rest. So really when you do work to create kinetic energy, you get this equation, 1/2 mv squared minus 1/2 mv naught squared, the starting kinetic energy. But that's going to turn out to be 0 because V naught is 0. So let's combine these two equations. We'll say that the force they apply times the delta x has to be equal to half of the mass times the V final squared, and we are looking for the distance, so I'm going to have to divide by the force. So if I divide by force on both sides, I get the distance that they pull this thing will be mv squared over 2f, and I can plug those things in. The mass that the work is being done on is 55,000 kilograms. That's a lot. I'm trying to think how many cars that is. Probably like 12, 20, I don't know. More than 10 cars. The V squared, so we've got a final velocity of 0.70 meters per second, which I will have to square, over the force, or 2 times the force, and the force that they are applying is 1,400 newtons. I'm going to write newtons as kilogram meter per second squared just so it's easier to cancel all my other units. All right, let's do this in the old calculator. 55,000 times 0.7 times 0.7 divided by 2,800. And I get 9.625. I get kilograms canceling. I have meters squared and seconds squared on top, so those will cancel. The second squared will, and one of the meters will cancel. So I should be left with meters, so this is all good. So 9.5 meters, a little over 9.5 meters. I think this is all 2 sig figs, so I am rounding to 9.6 as my final answer. 9.6 meters for those horses to get this thing up to speed, which is maybe 3/4 the width of a classroom, or the length of a classroom. So it doesn't take that much space in the grand scheme of things, but they're also not going very fast. They're not even getting up to what you and I would consider walking speed, which is like 1 or 2 meters per second. So there you go. Big heavy boat. All right, let's go do another one. Ranking tasks. Love some ranking tasks. We want to make biggest to smallest kinetic energy, and so I'll just remind myself that kinetic energy is 1/2 mv squared. And we're looking at, so 3 of them have the same mass, and 1 of them has twice the mass, so that one will have twice the kinetic energy, or at least that is as much as it would if they all had the same speed. But the speed factor is squared. We got to be careful. So if we look, I have a 2, a 2, and a 2. And even though this is a -2, that really doesn't matter for kinetic energy because it's getting squared. So kinetic energy doesn't matter what direction you're going. If you go to the right at 2 meters per second, or if you go to the left at 2 meters per second, you still have the same amount of energy. So keep that in mind. And then one of them is at 3. So between 2 and 3, that's actually a ratio of 4 to 9 because I'm squaring them. So, for instance, if I compare B and D, B has twice the mass, but D has twice the mass, but B has a 1.5 times the speed, which is a ratio of 9 to 4. So which is slightly more than twice. 9 to 4 is 2.25. So B will actually have more kinetic energy than D. And since B has the same mass as all the others, he's also beating A and C. So we'll say B is the greatest. So now let's compare. So A and C we can say are equal to each other because they have the same mass and they have the same magnitude of speed, and we're squaring it so that the negative sign does not matter. So what we really need to do is just compare C and D, because if we compare C and D, we've also compared A and D. So D has twice the mass, but it has essentially the same speed. So D will have more kinetic energy. So if I'm ranking, D beats A and C, and then A and C are equivalent. So there is your order. And we didn't even have to solve for kinetic energy. We can do it all with ratios. Good skill to have. All right. Baseball, okay. We're throwing it. We're throwing it at an angle. Oh boy, we love angles. And we've got 2 questions. How much energy does it start with, and what is the kinetic energy at the highest point? All right. So if I'm drawing this, when he throws it, or she, no gender, throws it at an initial velocity of 32 meters per second, and the angle is 30. But I told you that kinetic energy does not care about direction. There's no negatives in kinetic energy, and similarly, if we know that the total velocity, the vector velocity is 32 meters per second, we can just plug that in. So that's half times the mass of the ball, which is 0.15 kilograms, times that 32 meters per second, which we are squaring. That's all you need. That 30 degrees plays 0 part in the first question. So half times 0.15 and 32 and 32, and I'm getting this number, 0.76, nope, that is wrong. That is not what I'm getting. Get rid of that decimal. 76.8. And because it's energy, that should be in joules. All right. So this thing starts with, and I am rounding that to 2, so that's really like 77 joules if I round it. I'm going to keep the 76.8 in case I have to deal with rounding error later. But yeah, about 77 joules of kinetic energy this guy throws it with. So now the second question, which is what is the kinetic energy at the highest point of the arc? So let's think about that. What happens at the arc? Well, at the arc, it does this. It flattens out. So the speed at the arc will all be sideways speed. Essentially what happened is we started with this much sideways speed and this much vertical speed. And then at the arc we only have left this much sideways speed because it's not going up anymore. Well, notice that this is like a projectile problem if you're doing givens, that the acceleration is only in, so this is the x direction, the y direction, there's only an acceleration in the y direction of negative 9.8. There is no acceleration in the x direction. If there's no acceleration in the x direction, there's no force in the x direction, which means no work is being done in the x direction. Only work is being done in the y direction. So the y direction, work is being done to reduce that component until there is 0 kinetic energy in the y direction. So all the kinetic energy will be in the x direction, but it's not changing. Whatever kinetic energy we start with in the x direction is the kinetic energy that we end with in the x direction. Okay? So let's do that. Let's just find that speed, and we'll use that in our half mv squared. All right, what we have then, that's a cosine, because the 30 is an adjacent angle. So I'm going to oops, come on down here. We're going to have kinetic energy equal to half mv squared, which is going to be half, the mass is not changing, so it's still 0.15 kilograms. And the v squared, well, the velocity now is 32 meters per second at the peak times the cosine of 30. And that's what we're squaring. So let's plug that into the calculator. Half of 0.15 times, and then I have to do 32 cosine 30. And I have to square that. Let's see if my calculator will spit out the right answer. I think that looks good. Okay, 57.6 joules, which again, I'll round to 58 joules. And that should make sense. I had 77 to start with. I'm winding up with, I don't know, a little less than that. What, 4/5 of that? About. All right, not too bad. Those are kinetic energy problems. And hopefully this is going to give you some insight into solving your own kinetic energy problems.